In this video, I want to look at the diode under forward bias condition. So what we want to end up with is an IV characteristic, which is the current versus voltage characteristic for a typical diode, in this case the 1N4148 diode under forward bias conditions. And this is the curve that we are after here. And so what you can see is that as we increase the voltage across the diode, then basically when it reaches around 0.63, 0.65, the current really starts to increase. And this is typically how diodes behave. We usually use the value of 0.7 for silicon diodes, and around that turn on or that threshold voltage, basically the current really starts to increase. And so I want to walk through basically a schematic and then capturing some data and plotting it. Okay, so let's look at this basic circuit here. We've got a DC voltage source called VS. We've got a resistor just called R, diode called D. In LT-Spice, you can actually right-click and do Pick New Diode, and you can select from a list here. I'm using the 1N4148. You got many you can choose from in this list. So we'll just cancel that out. And the type of simulation we want to perform is what's called a DC sweep. So when you go to Edit Simulation command, you want to do a DC sweep, and the source that we want to sweep is the VS. This is our source voltage, and so this is the name of it, is VS. When we do a linear sweep, we're going to start at 0, end at 20, and go in increments of 0.1 volts. And so you can see that down here. Here's our simulation command showing us it's a DC sweep, and this is our source. This is our start value, our stop value, and the increments value. Okay, so pretty basic there. So if we go ahead and simulate it, it's actually going to show us on the horizontal axis. It's going to show us the source voltage, but that's not really what we want to see. What we're looking for, if you look back at our curve here, is we want to look at the voltage across the diode, okay, and the current through the diode, okay. And if you look here, we've got this resistor in between, right? So the source voltage is not going to equal the voltage across the diode because we have this resistor in between. Okay, so what you can do is set it up so that this voltage is what's on the horizontal, and then we'll just look at the current on the vertical. And so if we were to just, let's say, wave the voltage across the diode, okay, then we would see this. We would see that it starts out at 0, right? And basically it starts to increase, and it's approaching that 700 millivolts, okay, and that's where it's going to end up. And you can see even here when our source voltage here is all the way up at 20 volts, the voltage across the diode is pretty constant here, around 0.65 to 0.7 volts. But what we want to look at here is we have this designation for this node here. So this is V parentheses node 2. And so that node to ground, that's what we want to be on this horizontal axis. So what we can do is get rid of this. And if we right click here, we can say quantity plotted. We don't want to look at VS. We want to look at the actual voltage across the diode, which is in node 2 here. And this voltage here would also be node 1. Okay? And now we can just plot the current. And that's the curve there. Okay? So this is the same curve that we see here. Okay? And so basically as we increase the voltage, we sweep the source voltage. That's going to make the voltage across the resistor increase, which is going to make the current increase. And so we can see that current beginning to really increase there. Okay? All right, well, so what we can do now is basically extract the data here. And so if we were to look up here, we've got the source voltage, we've got VR, which is going to be the voltage across the resistor. IR is the current, okay? And using Ohm's law, that current is just going to be the voltage across the resistor divided by the resistor. And the power is going to be V squared divided by R. Okay, so here, the power here would be B2 times B2 divided by 1,000. Okay, so the power dissipated by the resistor and the current through the resistor are derived from VR. Okay, and VR is what we're going to get out of LT Spice. We're also going to extract VD and ID, which is the voltage across the diode and the current through the diode. Now it turns out, because this is a series circuit, right, the current through the diode and the current through the resistor, they should equal one another. Okay, so let's see how we would do that. So let's go ahead and get rid of that. And let's go to File, Export Data as Text. And you can see here that we have to select which ones we want to export. Okay? And so we definitely want the source voltage, okay, which will be node 1. Node 2 is the voltage across the diode, and then the current through the diode. We don't really need to extract these other currents because they're going to be the same. It's all a series circuit. Okay, so if we go ahead and select those three quantities, okay, and let's just go ahead and I'll leave the default there, and I'll just go ahead and replace it. Okay, and so that's going to export that data to a text file. And so that data is here. Okay, that data we just exported is here. So let's look at this. Okay. And if we look at this data, then we can see that actually we do have some redundant data, because it's actually, we have VS in the first column and then V node 1, which is the same node. Okay, V node 2 is the third column, that's the voltage across the diode, and then the last column is the current through the diode. And so all we have to do is just basically copy and paste this into an Excel file. and then we can work with the data and get our plot. Now, I mean, we've seen here that that basically we can just, all we really have to do is just plot it here, and I mean that's what we're ultimately looking for. But just wanted to kind of demonstrate how you could do this in Excel as well. So let's just create a new Excel sheet and copy and paste in this data. Okay. You can see that it's going all the way up to 20 volts, 2 times 10 to the first. So let's copy, let's get back to here and Control V, and we'll just paste in that data. And like I said, these first 2 columns are, they're just redundant because VS and node 1 are the same, they're the same node. So we can really just get rid of this column here. So we'll just delete entire column. And so now we're left with the source voltage, which we're sweeping from 0 all the way up to 20. And we're doing it in 0.1 increments. So that's why it's taking like about 200 rows to do that. Okay. And then we have the voltage across the diode and the current through the diode. And that is all we need to plot. And then we can fill in some other stuff here, like like I showed you earlier. You could calculate the current through the resistor using VR. Although I did not extract VR, I just got node 2 and then node 1, but I mean the voltage across the resistor is just the difference between those 2 voltages. So let's see, we could extract that as well. But I think for right now, I'll just go ahead and just show you how to plot these 2 on a scatter chart. So all we have to do here select that and you insert chart, and let's do XY scatter with smooth lines, and there we have it. So that shows us how we can that's how you can create a chart in Excel. You can do some stuff. You can change the title. You can also here you can add axis titles, right? So you could add here voltage across the diode. Of course, that's in volts. Current through the diode is in amps. Um, okay, so you can add titles there. Let's see what else. That's really the main thing. Let's see. You could play around with some other stuff. Shape outline. Well, you can kind of experiment, and make it kind of look the way you want. But you can change like the color. Um, you can change kind of the formatting. But the bottom line is that this is showing us the for a diode that's in being forward biased, that basically you start at 0, and as you increase, as the voltage across the diode increases, once you hit a threshold around between 0.6 and 0.7, you really start to see the current increase. Okay, and so that's pretty interesting. The other thing is, in this simulation, I went all the way up to 20 volts, and so you got to be mindful of the fact that in this circuit we have a 1K ohm resistor, and a lot of times, well, all the times that the resistor has a power rating in watts, and for a common power rating, is a quarter of a watt, so it's 250 milliwatts. So what I've shown here is that in the real world you wouldn't want to go above about 16 16 and a half volts on your source, because then you start generating a lot more power, or dissipating a lot more power, and so this gets above a quarter of a watt. So that's just something to be mindful of when you're doing a simulation in LT Spice. Then you can do that, but if you're really doing this on the breadboard with real components, you got to be mindful of the power rating and how much current that the circuit is going to draw. So that's something to be aware of. The other thing, I guess the last thing, just to kind of mention, is calculating the reverse saturation current. So I did a couple of calculations here. I got this information here from Wikipedia. So this is actually showing the equation, the diode equation, and you have the drain current, or sorry, not the drain current, the diode current. The diode current, not the drain current. That's for MOSFETs. So you got the diode current, you got the reverse saturation bias current, and that's what I'm trying to kind of show here, that you can kind of calculate this. It's very small. It's a very small number. And you've got the voltage across the diode, thermal voltage, which is approximately 26 millivolts, which is VT, and this N ideality factor. So 1 is for an ideal diode, and it can go all the way up to 2. And so what I did in the spreadsheet is just divide both sides of the equation by this term, and you can solve for IS. And so here, IS1 would have an ideality factor of 1, and this one would have an ideality factor of 2 here. And this would show you kind of what the reverse saturation bias current would be. And so if you look here, let's look here. You can see that for an ideal diode, it's much smaller. N equals 1 is for an ideal diode. And so we're looking here, I mean, this is 10 to the minus 13, very, very, very small number. Whereas for a practical diode, or one where N is maybe closer to 2, here you're looking, around nanoamps. So it's still a very, very small current. Nanoamps, right, as opposed to milliamps, which we would have under forward bias. So it's very, very small, but still different from N equals 1. And the other thing to kind of compare this with, you can see this is around 16 nanoamps. If we look at the data sheet for the 1N4148, you can see the reverse current is around 25 nanoamps maximum, 25 nanoamps. Now this is under a 20 volt reverse voltage, so there's some different values here. I mean, really high temperatures, it can be considerably higher. But if we just take kind of this baseline number here, 25 nanoamps, that's pretty consistent here. I mean, this is around 16 nanoamps, and of course for an ideal diode, it's much, much smaller. So on the order, 10 to the minus 14, as opposed to 10 to the minus 8. So anyway, that is just some things I wanted to present. Basically, how in LT-Spice you can do a DC sweep and sweep the voltage and observe the characteristics of the diode. So the voltage across the diode is going to increase to close to around 0.7, and the current will increase as well as we increase the source voltage. And so again, that's what we see here. Okay, and it's very easy to plot here, and then yeah, and then you can basically extract whatever information you want, export data as text. And I guess one last thing, which I thought of earlier, one thing you can do is actually, if we want the voltage across the resistor, well, the voltage across the resistor is this voltage, minus this voltage. And so what we can do, we could just plot that, VN1, comma VN2, and this would show us the voltage across the resistor. Well, that's with respect to the voltage across the diode. So I guess let's see. I think I'll just end there. I guess, I mean, if you wanted to, you could just end up plotting when you export the data. You could end up just, exporting both VN1 and VN2 and then subtracting them in Excel to get the actual voltage across the resistor. But that's, not probably all that necessary to do. So anyway, I think I'll just go ahead and end the video here. But I hope that was helpful. Maybe, just learning a little bit how to do some stuff in Excel. Here you can see you can just type in the equations. So here for, IS, these are the equations. You can just, type those in here. So here I used an N value of 1, and then this one over here is the exact same. It's just I changed the N value to 2. So yeah, so that's it. All right, I will just end the video for now.